I'm Ava, and today we're going to be going over the AMC 2026 problem set. So I'll be dropping these kinds of tutorials every 1 or 2 weeks, so feel free to drop a follow if you're interested in this type of content. But without further ado, let's get started on the first problem. Okay, so this problem tells us that what is the value of the following expression? So for these types of problems, what we can do is use brackets to block in each of the addition and the subtraction parts. And this way we can separate them so it's very easy to calculate, and we can easily, like, for example, 1 plus 2 equals 3, so that cancels out with minus 3. And 4 plus 5 is 9, which minus 6 equals 3, and so on. 15 minus 9 is 6, and then 21 minus 12 is 9. So then finally our overall, it comes down to 3 plus 6 plus 9, which we know is 9 plus 9, which is then 18. So then very quickly and very easily we can come down to the final solution, which is A, 18. Okay, problem 2. It tells us that in the array shown below, 3's are surrounded by 2's, which are then surrounded by a border of 1's, and what is the sum of the numbers in the array? So the image here, we notice that if we decide, we can actually split it up into regions like this, right? So then we would have, like, okay, we have 1's on the left and on the right. Then we have 1's on the top and the bottom. So this side we would have 3, and on top we have 1, 2, 3, 4, 5, 6, 7 1's. So then if we just like sum out how many of each number there are, and then we multiply by the value of that number, we can come down to the sum of all the numbers. So let's start with 1, right? We have 2 times 3 plus 7, and you can see this as a perimeter calculation, which is 2 times 10 equals, we have 21's. So how many 2's do we have? If you notice here, let's just like block it out in the same way. We have 1 2 on each side, and then 5 2's on the top and the bottom. So that comes down to 2 times 1 plus 5, which equals 2 times 6, which is 12. And then 3, just very easily, we can count 1, 2, 3. There are 3 different 3's, so that just comes down to 3. Alright, so then we multiply. 20 times 1 is 20, and then 12 times 2 is 24, and then 3 times 3 is 9. So we calculate that up, which is 44 and then 53. So we know the final sum should be 53. Okay, question 3. Haruki has a piece of wire that is 24 centimeters long, and he wants to bend it to form each of the following shapes, one at a time. So if we look at here, like, he wants to bend it, which basically means he wants to find the perimeter, and we need to verify whether or not the perimeter is less than or equal to 24 centimeters, if we wrote that out as an equation, as inequality. So here, the first one, it tells us that we have a regular hexagon and with side length of 5 centimeters. So we know hexagon means that there are 6 sides, which means this is like 6 times 5, right? And so that is like 30. And overall the perimeter is 30, which is wrong because 30 is larger than 24. And for number 2, it wants us a square, right? So square of area 36, we know that like the square's area is like the square of the side length. So we can find the side length by taking the square root of 36, which is 6. And then the perimeter is 6 times 4 equals 24, and that is viable. And then finally, like the third one, it tells us we have a right triangle whose length are 6 and 8 centimeters. So by the Pythagoras theorem, we know there are these like triangles of length 3, 4, and 5. And basically that is like 3 squared plus 4 squared equals 5 squared, right? And if we multiply by 2 on each of the side lengths, we can come down to a triangle of like 6, 8, and 10, because that's 5 times 2, right? And so then we know that this, like the perimeter of this right triangle is going to be 6 plus 8 plus 10, which is 24, so that is also correct. And in the process, you can actually come and go to the first one and just like cross it off so you don't forget. So then we know the solution should be D, which is square and triangle only. Okay, question 4. Brian's savings decreased by 20% in July and then increased by 50% in August. Now his savings are what percent of the original amount? So for these types of like percentage problems, something that you can think about is like percentage. It means like how much of 100. So basically it's very like connected with the number 100. So something that you can do very easily is you can start with 100, and then if we decrease it by 20%, that is essentially 100 minus 20, which equals to 80. And then increase it by 50%, because 80 is an even number. We can also just like fairly simply 80 plus 40 equals 120. And then if we bring that back and compare it to the beginning, because we used 100 as the initial number, it makes it very easy to calculate that overall this increased and was like 120% of the original amount. So problem 5, right? Casey went on a road trip that covered 100 miles, and she stopped for a lunch break along the way. The trip took 3 hours in total, and her average speed driving was 4 miles per hour. And in minutes, how long was the lunch break? Okay, so what does like this lunch break actually represent? So if we drew this as like a graph, which is not necessary in the competition, but for the sake of this, we'll draw it as a graph. And here we have on the bottom, the x-axis is time, and then the y-axis is distance, right? So essentially what this would look like is she would be moving at this like equal speed, and then she would come here to her lunch break, and she would just like stop and not move for a certain period of time. What time, we don't know, right? And then she would continue moving. So time in total was 3 hours. So you can think about it this way, is like how much time should she have moved if she had not stopped for that lunch break? And that would likely be like, if we look at the blue line, that would probably be something like this. And she should have been at this point. So if we can find how long that she should have been moving, we can find out how much time she was not moving for, because that is like the difference between what she should have reached and then like the blue line and the red line, right? So let's find out how much time she should have moved in 3 hours. So 40 times 3 equals 120 miles. And then how much did she move? In total, she moved 100 miles. So that's 120 minus 100 equals 20 less miles. And so that was the time that she was not moving for. And so because it's like 20 miles that she didn't move divided by 40 and then times 60 is the time that she was not moving for, which is half times 60, which we know is 30 miles, right? So 30 minutes. So then we know that she was not moving for 30 minutes, and that was how long her lunch break was. Okay, so the next question, question 6. Peter lives near a rectangular field that is filled with blackberry bushes, and the field is 10 meters long and 8 meters wide, and Peter can reach any black bushes that are within 1 meter of an edge of the field. The portion of the field that he can reach is shaded in the figure below, and what fraction of this area can he actually reach? So when you see this image, if we were supposedly going to like calculate this just directly the shaded area, then we would likely need to calculate 4 different areas. Well, that's like pretty time consuming, especially for the AMC 8. So if you see this as a whole, and you see the middle part as the part that you're subtracting, so that makes it a lot simpler, because you know that on the left side you have 1 meter, and you know on the right side you have 1 meter, and same for the top and the bottom, right? So if we can find that the width of this internal part is 10 minus 2, which we know is 8. And the same thing for the left side, it's 8 minus 2, which is 6, right? So we know that the internal area of this part that we want to subtract away is 8 times 6, which equals to 48. And so we can find out like 48 over the total area, which is 8 times 10, equals 48 over 80. And if we divide both by 8, we get 6 over 10, which we can simplify to 3 over 5. Now, importantly here, you want to remember that this is the part that he cannot reach, right? So he cannot reach this part. And we want to find that part that he can reach. So you got to make sure to, in the end, subtract 1 from this. Like subtract it from 1, which we get 2 over 5. So the answer is E. Okay. Miko would like to estimate how far she can ride a new model of electric bike on a fully charged battery. So she completed 2 trips, totaling 40 miles, and the first trip used half of the total battery power, and the second trip used 3 over 10 of the total battery power. How many miles can the electric bike go on a fully charged battery? So here it tells us like, okay, we have like 2 trips, but really what's only important is the total number of miles. Oops. So we can just cross out the 2 trips, as that's not very important for the calculations. So 40 miles is on like this certain number of battery power. So you want to find out how much battery power she's actually using to reach 40 miles. Because if we can then use that to calculate the total amount, it'll make it a lot simpler. So to find out how much battery power, we just simply add up 1 over 2 plus 3 over 10, which is 5 plus 3 over 8. Oh, sorry. Over 10. 8 over 10 equals 4 over 5. So we want to find out like how much would she use on 1/5 battery. Yeah, 1/5 of the battery. So that is 40 miles divided by 4 equals 10. And so then 5/5 equals 1 battery, like 1 full battery. We know it would be just 10 times 5 equals to 50. Okay, so next problem. Question 8. A poll asked a number of people if they like solving a mathematics problem. Exactly 74% answered yes. And what is the fewest number of people who could have been asked the question? So notice here, 74% is a percentage. And we know that percentages are of 100, so we can write that out into a fraction. So the bottom part here is how much number of people that you would have. Here we have 100 as the default, but we want to reduce that while still maintaining the same value. And so if you think back to like simplification, when you simplify a number from like, okay, 5 over 10, and that is essentially the same value as 1 over 2. So what we're doing here is we're maintaining this original value of 5 over 10, but we're like lowering and reducing the denominator. So we want to do the same thing here. And so we can basically just simplify it to like 37 over 50. And that would achieve the same value while still reducing the denominator. So then that means we know the final solution should be 50. Okay, next question, problem 9. What is the value of this expression? So this question is relatively easy in what you know you need to do. You just need to make sure that you do not have any silly mistakes. So as like context, we know that 16 equals to 2 to the power of 4, which equals to 4 to the power of 2. And 81 equals to 3 to the power of 4 equals to 9 to the power of 2. Right. So what we can do here is that if we're able to calculate this, we just need to make sure that we do every step very slowly and carefully so we don't mess up. Yep, so you would have a square root and then 16. And we take out and take apart the first one, but first let's write out the full equation. Okay, so the first step here is you would take apart like 81, right? So we know 81 is 3 to the power of 4, right? We have 3 to the power of 4. And so we just take that apart and it'll be like 3 to the power of 2. Okay, same thing for the bottom here, 81 times 2 to the power of 2. And then on the top here, you just have like 4 times 3, and then 9 times 2. And so importantly here, you can actually maintain this part since you don't really need to simplify it to its full like value and expand it to 9. It's a lot easier to just keep it as 3 to the power of 2. So then we just cross out and like simplify it. We get 2 over 3, which is B. Problem 10. 5 runners completed the grueling X marathon, and they were Luke, Melina, Nico, Olympia, and Pedro. So they tell us a few things here about like the order of these people. First, they tell us like Nico finished 11 minutes behind Pedro, and Olympia finished 2 minutes ahead of Melina, but 3 minutes behind Pedro, and Olympia finished 6 minutes ahead of Luke. It asks us that which runner finished 4th, and it's important here that you double check when you're doing your solution. So it looks like quite complicated because they give us 3 of these solutions. But if you think about a marathon as basically just a linear line where you have some people that are faster and then some people that are slower, then we can simplify this problem into just a timeline, which makes it a lot easier to calculate and think about. Okay, so we have our timeline here, and on the right side we're going to put the fastest people, and on the left side we're going to put the slowest people. So let's start first with like who's going to be our anchor, right? So if you look here, everyone seems to be finishing behind Pedro, right? So let's just put Pedro as our anchor. We put P here at the fastest for now. And okay, so first if we look at the first one, it tells us that Nico finished 11 minutes behind Pedro. So we'll put Nico like around here. The second one, it tells us that Olympia finished 3 minutes behind Pedro. So we'll put an O here and then 3. And 2 minutes ahead of Melina, which means Melina should be 2 behind Olympia. So here, 2. And then Olympia finished 6 minutes ahead of Luke, and 6 minus 2, right, equals 4. And so we're going to put Luke here, 4. And if you want, I guess you could put like 11 minus 4 minus 2 minus 3, which is 2 here. And then if you just count it over, like who's the 4th one, we can come relatively easy that 1, 2, 3, 4. So Luke is the final solution and as the runner that finished 4th. Okay, question 11. Squares of side length 1, 1, 2, 3, and 5 are arranged to form the rectangle shown below. And a curve is drawn by inscribing a quarter circle in each square and joining the quarter circles in order from shortest to longest. And what is the length of this curve? Okay, so if you look at it, you can see that as the problem told us already, these are all quarter circles, and then if you drew a full circle, it would kind of look like this. And so the first thing that we need to know is how do we find the distance of like this part, right? Which is basically the circumference. So we know that the circumference of a circle is 2 pi r, and this is for the full circle. But we only want to find a quarter of it, so we only want to find this part. But what we can do here is just like divide it by 4, and then very easily you can simplify it to pi r divided by 2. We keep that in mind when we're calculating these. We write it here like pi r divided by 2. We can very easily calculate all of these. So it'll just be 5 pi divided by 2, and 3 pi divided by 2, and then pi here, and then pi divided by 2, and pi divided by 2. So now we just need to add all of these up, right? So 5 pi divided by 2 plus 3 pi divided by 2. Plus we can write this one as equal to 2 pi divided by 2, just for the sake of calculating. And then we have pi divided by 2 and pi divided by 2. So that all comes down overall, if you count it up, this is like 8, 10, 11, 12. Comes down to 12 pi divided by 2, which equals 6 pi. And so we know that the final answer should be B, and that is the overall length of this curve. Okay, so question 12, right? It tells us that in the figure below, each circle will be filled with a digit from 1 to 6. And each digit must appear exactly once, and that is a pretty important requirement here. And the sum of the digits are in the neighboring circles. For example, these two should add up to be 6. And that's shown in the figure below. So what digit must be placed in the top circle? Okay, so for these types of questions, you have a pretty important restricting like requirement, which is that each digit can only be placed exactly one time. So that means that you have some very rigid like limits of the sums. So for example, the largest sum that you would have would be 6 plus 5 equals 11, and the smallest that you would have would be 1 plus 2 equals 3. So if we take that same idea and take that same logic and we take it into this problem, we can look at the largest and the smallest numbers shown in the neighboring circles, which here is 4 and 10. So this is not very, like, they don't easily tell us just 11 or 3. But if we look at these, there are only 2 solutions to actually solve these and to find the sum when you're restricted by this, right? Because you can't have 2 5s, so it can only be 6 plus 4 or 4 plus 6. So in a competition, you could just take a wild guess and choose one of these and try it out. So we take 6, 4, and then we have at the final part, we have 2 on the bottom, and then 3 here, 1 here, and then finally 5. If we verify here that, okay, 5 plus 1 does indeed add up to be 6, and so we know that this solution is valid, and that the top circle is filled with a 5. So then finally we come to the solution of 5. Okay, problem 13. They show us this square, and they tell us that it's made up of like unit squares that are kind of like not put straight, but they're slightly moved horizontally by half a unit relative to the row above it. So they ask us what is the area of the shaded square. So we know a square's area is A area equals the side length squared, right? So all we need to do is we need to find the side length, and at either of these sides, we need to find one of these sides. So let's go down here and we think about like Pythagorean theorem, right? You would have like a right triangle like this, and you would have like A and then B and C. So A squared plus B squared equals C squared. And if you don't know this concept yet, that's alright. You can search up like some tutorials online, and we take it back here, right? Because we know squares, they have right angles on each of their sides. Like all of these are right angles, and we can simply just like look at this side as like a triangle and have a right angle here. And we know the side lengths are 3 and 1. So this is the square root of 3 squared plus 1 squared equals square root of 10. That means the overall area is square root of 10 to like squared, and that equals 10. So the overall area of this shaded square should be A, which is 10. Okay, question 14. Jamie picked 3 equally spaced integers on the number line. And then the first 2 numbers add up to be 40. And the second 2 numbers add up to be 60. What is the sum of all 3 numbers? So let's just like draw like what would this number line look like? So you'll probably have a number here, x, and then you have 2 other numbers that are equally spaced. If we take the difference here to be r, we can represent each of these numbers as 2 variables, which are x and r. So x plus r and then x plus 2r. So let's take that knowledge that we have back to the bottom here, and we look at the first 2 numbers. The first and second numbers add up to be 40. X plus r equals 2x plus r equals 40. The second and third numbers are 60. X plus r plus x plus 2r equals 2x plus 3r, which is 60. So we know that 2r equals 60 minus 40 equals 20. And that makes r equal to 10. So we can bring that back in because we have our first equation of like 2x plus r equals 40, right? So that means 2x equals 40 minus 10 equals 30, and x equals 15. So So then they asked us, what is the sum of all three of these numbers? So you would have 15, and then 25, and then 35, right? But however, another easier way you can look at this is, we come back up here, right? You have actually 3 x's, x, 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 and then r and 2r. So that just means you have 3x plus 3r. So to find the overall sum, you just need to do like 3 times x plus r. And we know x and r are 10 and 15. So 3 times 25 equals to 75. So our final answer is 75, which is B. Okay, so Elijah has a large collection of identical wooden cubes, which are white on 4 faces and gray on 2 faces that share an edge. So he glued some cubes together face to face, and the figure below shows 2 of these solutions that he could glue together. The fewest numbers of cubes that he could glue together to ensure that no gray faces are visible, no matter how he rotates the figure. So let's think about what it actually means to like glue a cube together, right? So here he glues like this cube together, and if we look at what it's like when it's separated, you would have a white side here, and you would have a gray side here. So what you're essentially doing when you glue these 2 faces together is you're taking away both a gray side and a white side. So you're like reducing that number away. And then the problem tells us that we want to reduce it so that no gray faces are visible and with the fewest number of cubes. So what we want to do is we want to maximize every pair of sides that are glued together. They should both be gray. So basically you would be gluing only gray sides together, as that'll maximize the number of gray faces you can hide while minimizing the number of cubes that you actually use. So it's kind of hard to understand when I draw it here, but in your actual competition, or when you're doing it like in your own time, you can try and draw in a way that makes sense to you. But I'll show you what this would actually look like. So I draw the bottom 4 cubes here, and because we know that like every side, it needs to be connected by a single edge, right? So think about it here. Let's say we have a gray face on this side, and in these 2 cubes, the 2 cubes that are like further from us, they are connected based on this side, right? And so each of these cubes need another gray side. So let's put the gray side here, because we want to reduce the number of visible gray sides. So we have 2 gray sides that are here. And so that means that like these 2 cubes, the cubes on the right side, are connected via this face, and the cubes on the left side are connected via this face. And so then each of these 2 cubes that are closest to us, they also need a gray face between them. So we put this gray face between them. That means like this cube here and this cube here is connected via this gray side. So if that makes sense, basically what you do is you keep all the gray faces within this part and within these 4 cubes. And so essentially in the end, we only have 4 cubes that we need to cover all the gray sides. Okay, problem 14. Consider all the 4-digit integers consisting of only even numbers, only even digits. What fraction of these are divisible by 4? Okay, so we know that like when a number is divisible by 4, it means that like the last 2 digits are divisible by 4 as well. So what this means is basically, if we look at some examples, I'll give out some numbers like 1, 2, 4, 60, and then like 21, 22, 32, and 04. So if we look at the first one here, we know that 24 is divisible by 4, as this 24 is 4 times 6, right? So this makes the whole number as a whole divisible by 4 as well. And if we verify that, 124 divided by 4 is 3 and 1. So that means that it works, right? And then 60 is also divisible by 4, and so the whole number is divisible by 4. 21 we know is not divisible by 4. And so that means the same thing would apply for 121 or 221 or so on, as all of these numbers have 21 as their last two digits, making them not divisible by 4. 22 is the same logic, it's not divisible by 4. And 132 is because 32 is divisible by 4. And for single digit numbers, we look at this as a whole, and that makes this divisible by 4 as well. So if we move back to our original problem, only consisting of even digits means we only have the digits of 0, 2, 4, 6, and 8. And because these are not that many digits, what we can go ahead and do is just list out all the possible combinations of 2 digits between these 4 digits. Okay, so now we have all of these different two-digit numbers. And so we can go through them and cross the ones that are not divisible by 4. And if you do this fairly quickly, you'll realize that in each row, there's only 3 combinations that are divisible by 4. So that kind of comes down to only 3 out of 5 can. And then some people, they might go ahead and then keep finding how many of these I don't know, the first 2 digits are how many combinations of these exist. However, that would be that's not completely necessary for this problem because it's asking you what fraction of these are divisible by 4. So if you look at it these first 2 digits, you think of them as not really changing because regardless of whether or not your last digits are divisible by 4, these first 2 combinations, the combinations of the first 2 digits are going to be the same across all the 4-digit integers. So that is, we don't need to calculate that, and we can just take 3 over 5 as the final answer. Okay, so problem 17. 4 students are arranged in a row, and they travel to people sitting next to them and then rearrange themselves so they're no longer seated next to any of the same people. How many rearrangements are possible? So we can call these people A, B, C, D. And because they cannot sit next to the people that they've already sat next to before, let's look at the 2 people in the middle here. B and C. So B and C have both sat next to 2 people. For example, B has sat next to both A and C, which means B can only sit next to D here. And for C, it can only sit next to A. So that means that these 2 people, they're gonna have to be sitting on the outside because they can only sit next to one other person. So we draw that out, right, we can draw that, write that out first if we have B on the left side and C on the right side. So let's come back up here and see is that B has already sat next to D before, which means B can only sit next to, B has already sat next to A before, so B can only sit next to D. And so we put D here and we put A here. Now remember here that you gotta swap it over, and so that gives us another combination, which is C on the left side and then B on the right side. And so we can put A here and put D here. And overall it comes down to 2 different combinations and arrangements. So question 18. In how many ways can 60 be written as the sum of 2 or more consecutive odd positive integers that are arranged in increasing order? So consecutive odd positive integers, what that means is that between each of these integers, you're going to have a gap of +2. So if you write that out as an arithmetic sequence, you would have A as the first one, and then A plus 2, and then A plus 4, and so on, until you would eventually reach a number which is A plus 2 times n minus 1, where you have a total of n numbers in total, right? So we write that out using the arithmetic sequence sum. We would have A plus 2n minus 2 divided by 2 times n, which equals 2a plus 2n minus 2 divided by 2 times n, which comes down to 60, right? And so if we simplify that a bit by dividing this chunk of the fraction off, we would have n times a plus n minus 1 equals 60. And so let's look at here, right? we only have one equation. However, we have two different variables. And so we know that if you want to have two variables, you're going to need two different equations. If you have three variables, you need three equations. But actually, this is solvable because there's an implicit assumption here, which is that like on parity, right? So if we look at the parity of these numbers, we know that A has to be odd and that this thing, 60, is even. And so let's assume if n is odd, what would happen? If n was odd, you would have an odd number times odd plus odd minus odd. And so that comes down to an odd times odd equals an even, which is something that is not possible. So that means this is crossed out and that n has to be even. So now if n is even, what we can do is we can start from 2 and just go up through all of the even numbers and solve it accordingly, keeping in mind that A does have to be odd, and so that would be our solution to check. If A is not odd, then the solution is not correct. So let's start out, and we have here n and then A plus n minus 1. We start out with n equals 2. And then we do some quick like subtraction. This has to be like division, and this has to be like 30. So let's come over here and solve for n plus a. So if n here is 2, and then we bring it back up, this has to be 30, and n is 2. So 2 minus 1 equals 1, which means a has to be 29. So we get 2, 29. And because 29 is odd, we know that this solution is correct. Now we continue in the same manner. 4, 15, and then this thing here would be like 4, 12. We know that's wrong since 12 is not an odd number. And then 6, 10. We get 6, 5, which is we know is correct. And then like you can keep going in like 10, 6, but that's not correct. Since if you bring it back up here, you'll realize that this will make a negative number, so that would not be viable. So then overall, if we count, we have 1, 2 solutions, and that means there are 2 ways to arrange this in increasing order. Okay, next, problem 15. Miguel is walking with his dog, Luna, and when they reach the entrance to a park, Miguel throws a ball straight ahead and continues to walk at a steady pace. Luna sprints towards the ball, which stops by a tree. And as soon as the dog reaches the ball, she brings it back to Miguel. And Luna runs 5 times faster than Miguel walks. What fraction of the distance between the entrance and the tree does Miguel cover by the time Luna brings him the ball? So, like something that's very helpful here is to give us this like image of what this would look like. They give us the path, right, of each of these two entities. So Miguel goes here, and he kind of just stops there because Luna runs all the way back and meets him here. So if we take the distance and we assume that this is like distance equals, let's write it first out as d. And you'll notice like, because this whole thing is actually equal to like d. But you notice that they ran twice, right? In total, Luna runs 1d, and then she helps Miguel to make up for the second d. So the total path that they're actually walking is 2d. And so we can write this out like this. X plus 5x equals 2. And here we actually remove this variable here because there is no requirement for this. So if we just like take away this variable and assume d equals to 1, it'll make calculating it a lot easier. Since we only need to find like the what fraction, right? So we don't need to actually find the real distance as a number. So that comes down to 6x equals 2, and x equals 2 over 6 equals 1 over 3. And so we know that Miguel walked a third of the distance to the tree. Okay, so the land of Catania uses gold coins and silver coins. Gold coins are 1 millimeter thick and silver coins are 3 millimeters thick. In how many ways can Taylor make a stack of coins that is 8 millimeters tall using any arrangement of gold and silver coins, assuming order matters? So we can take this and like take the number of gold coins as x and the number of silver coins as y. And so that comes down to like x plus 3y equals to 8. And here, because the numbers are relatively small, we can do is we just create a table with the number of x and the number of y. If we take this to be 0, then x would have to be 8, because 1 times 8 equals 8. And we take this to be 1, then x would have to be 5. Take this to be 2, x would have to be 2 as well. But then notice here that it asks us for what is the number of arrangements. What arrangements means is that you could potentially have something like gold, gold, silver, and this would be different from gold, silver, gold. And so we need to find a number of permutations, not just the combinations. So, right, let's see how many of these can have permutations. This can only have one, since you have all of them are silver coins, and we assume that coins are the same thing, and coins are not like different like people, right? So that's 1. And then 5, this is 6. Since you're finding like out of 6 total coins, I want to place 1 single gold coin. So that's 6. And here is 4 times 3 divided by 2 equals to 6. So the final solution is 6 plus 1 equals to 13. So then we get that overall solution, which is D of 13. So question 21. Charlotte the spider is walking along the web, shaped like a 5-pointed star, shown in the figure below. The web has 5 outer points and 5 inner points. And each time Charlotte reaches a point, she randomly chooses a neighboring point and moves to that point. So Charlotte starts at one of the outer points and makes 3 moves. Revisiting points is allowed, which is important. And then what is the probability that she is now at one of the outer points of the star when she finishes all her moves? So let's take this top one as a starting point. So you notice that you can only go from in to out. So what this means is you can't walk from an outer point to another outer point. That's illegal in this situation. So if you want to reach like an outer point like this, you have to go from all of these 5 inner points. And so what that tells us here is that if she starts at this outer point as her initial point, she starts at an outer point, then she can only go to an inner point. And from an inner point, she can choose to go to an inner point or to an outer point. But because she wants to reach an outer point as the last solution, it means that in the middle, she must go to an inner point. So that tells us a few things, right? If we view this, the first move as blue line, second as a green line, and the third as a purple line. Let's start from the blue line, assuming that she wants to reach an outer point at the end. So she starts here at the top. She has 2 solutions. You can go down to the left one, the left inner point, or the right inner point. So let's say she goes to this one as her first position. For the second, she can go to either this inner point or this inner point. Let's say she goes to this inner point as her second location. And then finally, she has 2 solutions, 2 choices of outer point. She can go to this outer point, or she can go to this outer point. And so let's say she chooses this outer point, right? So what we notice here is that each path, assuming she takes, and she has the goal of reaching an outer point, she has to take 2 paths and take 2 choices at every turn. So in total then, how many, we can write that out as a probability. 2 times 2 times 2, since she has 3 moves, and at every move she has 2 choices. So then what are the total number of choices that she has? Well, if we look at this graph, right, from the first point, she still only has 2 different places that she can walk to. So for number 1, that's still 2. But for number 2, if she goes here, she can go 1, 2, 3, or 4. So she has 4 different places that she could potentially go. So 4. And for this final third move, it is also the same logic. She has 4 different places that she can go. 1, 2, 3, and 4. Notice here that like revisiting points is allowed, which is why she could potentially go backwards like this. Okay, so then we have at the top is 8 and on the bottom is 32. That easily comes down to 1/4 as our final probability. So problem 22. The integers from 1 to 25 are arbitrarily separated into 5 groups of 5 numbers each, and the median of each group is identified. So let m equal the median of the 5 medians. Median of the 5 medians, right? So what is the least possible value of m? So let's recall what a median means. So let's say we have 5 numbers. 1, 2, 3, 4, 5. Each of these are numbers. So these would be sorted in increasing order. So for example, you would have like a 5 here, and then you would have the first one would have to be 1, and the last one would have to be 5, right? And so the median is a number we take in the middle, and it is like the middle number when you sort all the numbers up. And because it is currently only an odd group, we can just consider that single scenario, and we don't have to worry about like averaging the middle or so on. So if we draw this out, right, and we draw an individual group out, you would also have 5 numbers, and you would have this number to be the median. And you have 3 numbers that are less than or equal to m. And since we want to find the least possible value of m, we can assume that these 3 numbers are like 3 numbers less than or equal to m. So now we look at all of these medians combined together. We have median 1, median 2, 3, and then 4, and 5. And as well, these are sorted in increasing order. So if we want to find what median 3 is, we know that within each of these 3 groups, you have the same calculation, which is 3 numbers less than or equal to their median. So we take that up here, it would be 3 times 3 of these less than or equal to our uppercase m, which is our final solution. So that equals to 9, and assuming that we take the least possible value, that means our least possible value should be 9. Okay, problem 23. There are 5 round coins of diameter 4 centimeters. She arranges the coins in 2 rows on a tabletop as shown below and wraps an elastic band tightly around them. In centimeters, what would the length of the band be? So when you're looking at these problems, like at first glance, they look very complicated. Like, what can I do with this? But first, what you can do is you connect all the centers of all the circles, and that'll make all these lines become more apparent, and it'll be easier to calculate. So let's connect all of the centers of each of the circles. We can connect these two, and then okay, so now we have connected all of these centers, and let's just like move these lines up parallel to the top so we can find the actual length of these. So notice here that this would be like a right angle, and that these two would be like parallel. So we did that for all of these. Let's come back here to the diameter and be careful about the wording. This is a diameter, which means the radius equals to 2. So we take that up here, and then we know that this is like 2 plus 2 equals to 4. And so this is of length 4, and this is also 4. This is also 4. On the bottom, this part is 8, so that's 8. Okay, so now we have these like random pieces of the square, and we find it like very difficult. Like, I don't want to calculate the angle of this because that would be complicated and very like convoluted. So let's just think about, like, these are all parallel lines. So what if I like move this line down? What would it actually look like? So let's draw this line down all the way to the bottom. Now notice here how these are actually parallel. And so essentially what you can do is you can move this small piece all the way down to here. So that would look like doing this. Have this line, right? And so that whole thing actually forms a 180-degree angle. And the same thing would occur for this side, where you have a 180-degree angle. So you have a radius 2, and you want to find 2 pi r, which is the overall circumference, and that would equal to 4 pi. So we know what the circle parts add up to, and we also know what the constant parts add up to. So all we have to do is add up all of these parts and we'll get our answer. So that would be 4 plus 4 plus 8 plus 4 plus 4 pi. So that adds up to 20 plus 4 pi. So overall we get the solution of C, which is 4 pi plus 20. Okay, problem 24. The notation n plus reads n factorial and is defined by the product of the first n positive integers. So define the superfactorial of a positive number to be like the product of the factorials of the first n integers. How many factors of 7 appear in the superfactorial in the prime factorization of the superfactorial of 51? Yeah. So think about it this way, right? 51. And 7 has factors along like this. 7, 14, 21, and 28, and so on. So if we can split these up, we can find within each of these ranges how many different 7s there are. So what this looks like is you would start at 1 factorial to 6 factorial. And if we multiplied all of these up together, how many factors of 7 would there be? There would be 0 because you don't have any 7s yet. And 7 factorial to 13 factorial, that would be 1 times 7, since you have 1 7 within each of those, and that comes down to 7. And if you have 14 factorial to 20 factorial, that would be 2 times 7 equals to 14, since you have now like 7 and also 14. So that is like 2 factors of 7. So you just continue doing this for all the different ranges, and then in the end you can add them up together. So this would be 21, and then 28 factorial to 34 factorial would be 4 times 7 equals to 28, and then 35 factorial to 41 factorial would be 5 times 7 equals 35. Then 42 factorial to 48 factorial would be 6 times 7 equals 42. So now here's like a tricky part. 49 factorial to 51 factorial. So now why is this tricky, right? So the reason for this is because 49, it actually has 7 squared. It's equal to 7 squared. So that means it brings not 1 factor, but it brings 2 factors of 7 back. So instead of this being 7, you would make it to be 7 plus 1 equals 8. What this means is that all the factorials like 49 factorial, 50 factorial, and 51 factorial, all of these, they have 8 factors of 7 rather than 7. So that means it should be like 8 times 3 equals 24. So the rest of it is just simply adding it up. 21, 42, 70, 105, 147, and then 171. So that comes down to the final answer, which is 171. Okay, so problem 25. This is one of the harder problems in this problem set, as it's the last one. But it tells us that in an equal angular hexagon, all interior angles measure 120. An example of such a hexagon is the one shown below, with the side lengths of 2, 3, 1, 3, 2, and 2. And this is inscribed in an equilateral triangle, ABC. Consider all equal angular hexagons with positive interior sides that can be inscribed in ABC, with all 6 vertices on the side of the triangle. What is the total number of such hexagons? And they cannot only differ by rotation or reflection. Okay, so a common pattern in these types of like equal angular hexagon problems is that if we zoom into the top here and we draw out this angle as 120, this means this angle will be 60, and then because they're supplementary, and then this is 120 and this is 60. So what this means is that essentially all of these little like spikes that you see, like little triangles at each side, they're equilateral as well. So what you can do here is we write out that this equals to C, and this equals to B, this equals to A, right? Let's write it out in red. C, B, and A. That means that this equals to B, this also equals to B, and this also equals B, and so on for all the other sides. So now we can also write out this number as X, this number as X, this number as Y, this number as Z, which is like this side. So this gives us a few different equations that we can use. The first being that we can actually first find out the side length equals to 6, and this is the same for all of these different equilateral hexagons, as they all have to fit within this specific ABC triangle. So that gives us the equation of A plus X plus B equals B plus Y plus C equals A plus Z plus C. So if we write this out as having the variables X, Y, and Z as the primary variable, we get this series of equations. X equals S minus A minus B, which is larger than or equal to 1, since they all have to be positive integers. And then Y equals S minus, yes, equals S, equals S minus B minus C, which is larger than or equal to 1. And Z equals S minus A minus C, larger than or equal to 1. So we have these three equations, and if we convert this to A plus B, we get A plus B less than or equal to S minus 1 equals 5. And then B plus C less than or equal to S minus 1 equals 5. And then A plus C less than or equal to S minus 1 equals 5 as well. So now we can assume something here to make the solution a bit more simple. Assume that A is like the smallest, B is the middle, and then C is the largest number. So because we have 5 as this, and because C is the largest number, we can start out with the number 4. So if C equals 4, and then B can only equal 1, since it has to add up to be less than or equal to 5. So we get the solution of 1, 1, 4, since A also has to be less than or equal to B. So we do the same thing for all of the C's, using C as our anchor for this problem. Because if C equals 3, if B equals 2, we get 1, 2, 3, and then 2, 2, 3. If B equals 1, we get 1, 1, 3 as our only answer. If C equals 2, if B equals 2, we get 2, 2. Oh, wait, no. We get 1, 2, 2. And then same thing here, 2, 2, 2. If B equals 1, we get 1, 1, 2. And finally, if C equals 1, then B has to equal 1, and we get 1, 1, 1. So yeah, then we get all of our solutions here, and notice that this is like a very systematic way of looking at it. So you start at the largest C, and then you go down 4, 3, 2, 1. And by going down through this order, it ensures that you don't miss any combinations. And same thing for the B's. You start from the largest possible, and then you move on to the smallest one. So this ensures we don't lose any number of solutions. So finally we come down to 1 plus 3 plus 3 plus 1 for each of these. It comes down to 8 total solutions. So we know that our answer should be E, which is 8. Okay, thank you guys so much for listening. And this is our final problem of this year's problem set. And if you have any problems or any questions, you can just leave a comment below, and I'll try to respond to all of you. And thank you so much for watching. Bye bye.